This is section 2.6, Proving Geometric Relationships. In this section, we're going to learn about two different types of proofs. So we've already done two-column proofs, and now we're going to learn two different types of proofs. The first one is a flowchart proof. It's a proof that uses boxes and arrows to show the flow of a logical argument. So it's basically a two-column proof just put in a visual way showing what direction things go. So remember, the first statement is always your given. So we have our statement and then our reason is underneath. And then we go from there, keep going until we get to our proved statement. A new theorem we have is theorem 2.3, which is the right angles congruence theorem. The right angles congruence theorem says that all right angles are congruent. There's a proof for you right there to show that this is actually true. And since it has been proven and what's given to us as a theorem, we can now use it as one of our reasons in a proof if it works. So let's complete this flowchart proof. Okay, so we're given that AB is perpendicular to BC and DC is perpendicular to BC. We're trying to prove that angle B is congruent to angle C. So our first step is always our given. And then now we know that we're using the definition of perpendicular lines, so thinking what perpendicular lines mean. Okay, if they're perpendicular, that means they meet at a right angle. So I can say that angle B and angle C are right angles, because that's what the definition of perpendicular lines means. And from there we can say that angle B is congruent to angle C using the right angles congruence theorem that we just learned. So right angles congruence theorem. Because remember, that tells us that all right angles are congruent. A couple more theorems. They're very similar. One's about supplements, one's about complements. It just says that if two angles are supplementary to the same angle or to congruent angles, then they are congruent. So if 1 and 2 here are supplementary and 2 and 3 are also supplementary, then 1 and 3 are congruent. The same thing works with complements. If 4 and 5 are complementary and 5 and 6 are complementary, then angle 4 has to be congruent to angle 6. Our second type of proof that we're learning about today is a paragraph proof. It's just a proof written as a paragraph. So fun fact, the longest proof began in the 1970s and was worked on by 100 mathematicians, and it took over 30 years to complete. It's 15,000 pages long, and that does not include the 1,200 page guide. So if you ever think about complaining that your proof is too long, just remember that it's not 15,000 pages long. More postulates and theorems. Postulate 2.8 is the linear pair postulate. So if two angles form a linear pair, then they are supplementary, which makes sense because by the definition of linear pair, they add up to 180, or they form a line. We know a line is 180 degrees, and we know that supplementary angles form 180 degrees. Our next theorem is theorem 2.6, that vertical angles congruence theorem, saying that vertical angles are congruent. So that's saying that 2 and 4 here, since they're vertical angles, they are congruent, and that 1 and 3 here are congruent. This theorem is kind of an extension of our congruent supplements theorem. So 2 and 3 are supplementary, 3 and 4 are supplementary, so 2 and 4 have to be congruent. So here's an example of a paragraph proof. I'm not going to read it to you. If you want, you can take a second to read it yourself. And here's a proof. Let us finish this proof. So we know that AB is equal to DE and BC is equal to CD. And we're trying to prove that AC is congruent to CE. So always, 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 our first statement is what's given to us and our reason is given. So statement 2, AB plus BC equals BC plus DE. All we did is we took this and we added BC to both sides, so that's the addition property of equality. From there, we can say that AB plus BC is equal to CD plus DE. Because we know BC is equal to CD, we can substitute them for each other. So that's the substitution property of equality. Then we have that AB plus BC equals AC, and CD plus DE equals CE. Well, if we look, AB plus BC here is that AC. CD plus DE equals CE. That's our segment addition postulate. Remember, part plus part equals whole. And then we need to use the substitution property of equality. Okay, so I want to look at 3 and 4 right now and use the substitution property. Well, I see AB plus BC here. I know that's equal to AC, so I'll substitute that in. And I know that CD plus DE is equal to CE, so I'm going to substitute that in for that, because that's starting to look more like what we want to prove. Then, once we know that their lengths are the same, we can say that they are congruent by the definition of congruent statements, or congruent segments. Because remember, the definition of congruent says that they have equal measures, so it goes back and forth. We can say, if we know they're congruent, we can say that their measures are equal, or if we know their measures are equal, we can say that they're congruent. All right, last example, find the value of x. This is going to use our vertical angles congruence theorem. We know that vertical angles are congruent, so I can say that 3x plus 1 is equal to 148. Solving by subtracting 1, 3x equals 147. Divide by 3, x equals, I believe, 49. You can go ahead and plug that in back for x to see that 3x plus 1 is equal to 148, but you should find out that that does work.